Thank you for joining Realty BBL webinar. My name is Kazumi Nishikawa, Principal Director, Economic Security Policy, Minister Secretariat, Ministry of Economy, Trade and Industry. I'll be serving as a moderator of today's presentation. Today, we are truly honored to welcome Dr. Mukesh Khare, General Manager of IBM Semiconductors and Vice President of Hybrid Cloud Research at IBM. Dr. Khare will deliver a lecture titled, What is Supply Chain and Technological Basis for Economic Security, especially securing the future of computing. I myself appreciated a lot to the Dr. Mukesh Khare with regard to the semiconductor policy, as well as the AI and quantum development. So I personally really enthusiastic today to listen to Dr. Khare's presentation. We will have roughly 40 or 45 minutes presentation from him. Then after that, followed by Q&A sessions until 1:50 p.m. So let's start. Dr. Khare, please start your presentation now. Thank you.
Thank you very much, Nishikawa-san, for kind introduction and inviting me to share IBM's view on the future of computing. It's truly our honor. I will start with a little bit of background of IBM and IBM research. IBM is the only IT company which is more than 100-year-old in the whole world. And the reason IBM has survived for more than 100 years is because of IBM research, because we are focused on inventing future of computing. We have, as you can see, we are a global research organization with research sites all over the world. Our headquarters is in New York, and we also have a very large research facility in Tokyo, as well as in Kawasaki, where we perform different research in computing. Along the way, IBM has won many awards because we are very academic research, which is applied to industry for computing. So it's both long-term research, but with an outcome for business. Both are important to IBM. Right now, I will say we are living in a very, very exciting and very unique time in the era of computing. There are three parts of computing that are really coming together in front of our own eyes. The traditional computing, or we call it bits, which is high-performance computing, transaction, high-precision computing. That has been there for a long time. And that is continuing. It's not going away. It will continue. A new form of computing, which we call neuron, or the AI computing, is really taking off. And this is a very exciting time for AI to be the next workload to drive computing in the world. And the third part of computing, we call it qubit, which is quantum computing, which is also coming in the pipeline. So we are in an era where three forms of computing is coming together: the traditional high precision, high performance computing, the AI computing, and the quantum computing. So in the future, all three computing will coexist. It's not one will replace another. They will all add to each other. And computing will be consumed with hybrid cloud. Hybrid cloud is very important because there will be some cloud which will be public cloud, some will be private cloud, some will be on-prem. So there has to be a common fabric for consumption of computing. So this is where the industry is going. And today I will go a little bit more deeper into AI part, because AI part of computing is really taking off. To give you a perspective, generative AI is so important now in the world, and there is a projection that it can raise global GDP by 7% in next 10 years, like by $9.5 trillion. Think about it. When do we come to be at the beginning of such a big transformation in the world of computing? And I will share with you that we are just getting started in the AI computing. It's not that AI computing is complete. AI computing is just getting started. So we have so much opportunity ahead of us to be participating in creating technology and creating sustainable technology, because these computing requires a lot of energy as well. To give you an estimate, the rate at which AI workload is growing, on the left-hand side, just to give you an estimate of the size of model that are being prepared or produced, large language model for AI, they are growing almost exponentially. These days, most advanced AI models are using as much as 500 billion parameters. That means the demand for computing is almost doubling every 3 months. We are used to Moore's law where, computing doubles every 18 months. Now the demand for computing, for AI computing, is doubling every 3 months. That's huge. However, it also generates a very large carbon footprint. To give you an example on the right-hand side, just for training one GPT-3 model, which was produced in 2020, 3 years ago, it generates as much carbon footprint as 3 round trip between New York and San Francisco. On one hand, there is a huge opportunity. On another hand, we have to be careful about carbon footprint, the sustainability associated with creation of this technology. So that's that's an opportunity, and that's a challenge in front of us as a society. At the foundation of all of these things is still the semiconductor technology. And I wanted to emphasize that semiconductor technology is the one that will enable all of the computing that I talked about. Now let's look at the semiconductor technology itself. Right now, the technology, the largest chip use as much as 20 to 50 billion transistors on one chip. But semiconductor industry is heading towards a 1 trillion transistors on a chip by the end of this decade. That means there is so much innovation ahead of us. For the next era, for continuous growth of semiconductor industry, the next era will be driven by AI. AI, artificial intelligence, is the workload that will drive innovation in semiconductor industry. And that is how semiconductor industry and AI are connected, because all the AI models are built on semiconductor chips. That is at the heart of it as well. We have worked with the lithography era, where scaling was driven by miniaturization of dimension. Then came we are driving now new transistor structure era like nanosheet. Another era in semiconductor that is evolving is associated with chiplet technology. Chiplet technology, where you can mix and match chiplets which perform different functions, even at different nodes, are going to be one of the accelerator to get us to the 1 trillion transistors on a chip by end of this decade. Also to mention, semiconductor industry today is about $600 billion industry. By the end of this decade, semiconductor industry is projected to become a $1 trillion industry. So both $1 trillion industry and 1 trillion transistors on a chip. That is how semiconductor industry is growing. In order for us to develop such technology, we need partnership. Partnership between government and private sector and university. All of us have to come together. It's very difficult for one company or one university to do all of it together. We at IBM are very fortunate that we are participating in one of the largest and I will say most advanced research and development center in New York, in Albany. It's called Albany Nanotech, which is a partnership between IBM and New York State. New York State has an entity called NY Creates, which provides the infrastructure for all of us to work together. We have, as you can see on the right-hand side, we have a large number of ecosystem partners. Almost all of the ecosystem partners, we work together to create technology for the benefit of all of us. We had partnership with Samsung in that facility for almost last 20 years. And we are very proud to welcome Rapidus, Japanese company, or the new Japanese foundry to build leadership technology in Japan. We have many Rapidus engineers who are working side by side with IBM engineers to create 2 nanometer technology and beyond. This facility also has some of the most advanced tooling capability, like today's EUV lithography tool that you can see on the left-hand side. As a part of this big collaborative ecosystem, we are very proud that IBM, in partnership with many partners that I have listed on the previous page, we created world's first 2 nanometer chip technology. We announced that in 2021, and we are very proud to be partnering with Rapidus to support their ambition to become one of the world's leading foundry in logic technology or advanced logic technology. This technology provides as much as 75% less power consumption compared to today's 7 nanometer technology. It's very important that we keep that in mind. This technology uses a new device structure called nanosheet device structure. You can see it on the right-hand side, some of the cross sections. And to give you a context, that each sheet that you see on the right-hand side, its thickness is about 4 nanometer, which is of the size of a couple of DNA molecules in human. So we are talking about an extraordinary scale that has never happened. This technology also won the Time magazine's Best Invention of 2022 award last year. Creation of such technology and beyond in semiconductor requires a public and private partnership. And I'm just coming back from New York, where we announced just on Monday another large partnership between New York State, IBM, Micron, Tokyo Electron, a Applied Materials and others to invest $10 billion to continue to have more advanced capability, especially to enable high NA EUV lithography capability. This will be world's first such capability in a public-private partnership, which is open, where key partners can participate and develop next technology 1 nanometer and beyond to support the need of AI workload. It's important to connect that all these investment and this technology, the center that we are creating, will continue to fuel the compute demand for AI that is driving the demand for semiconductor. So those two are continuously connected. And we are very proud that many Rapidus engineers are participating at Albany Nanotech facility under the high-level partnership between cooperation between US and Japan in semiconductor. Now I will switch to AI. It's always important to understand semiconductor is at the heart of what will happen in the world of computing, which is the AI, which is really taking off. We were, at IBM, we are very fortunate that we work on every aspect of computing stack. We get to work on process technology, like what we do with, we are working with Rapidus as an example. We also get to work on chip technology, chip design. And we also work on software and system design. And it's very important that in the world of AI, we look at end-to-end. We look at every part of the stack, and I'll describe that to you a little bit more. In computing, the value will come from every part of stack. Value will come from semiconductor, value will come from chip design, value will come from software, and value will come from system. So we looked at AI hardware initiative as full end-to-end. We call it a full stack approach, where you start a silicon wafer and you can run a AI workload end-to-end. We started this partnership. IBM always believes in collaboration. So we started this partnership in collaboration with commercial, academic, and government partners. As you can see, we have several locations who are participating in this initiative as well. Locations in US, as well as we have a location in Europe, in Zurich, Switzerland, and Tokyo, Tokyo and Shin Kawasaki locations, which are providing valuable technical input into AI Hardware Center initiative. Our AI Hardware Center initiative includes 4 areas. Course and architecture, that is very important, that's on the design side. Heterogeneous integration, as I described, the era of AI in semiconductor will be driven by heterogeneous integration and chiplet technology. So it's very important that we focus on the chiplet and the heterogeneous integration as a part of AI Hardware Center initiative. We are also looking at long-term projects like analog elements. I will describe that a little bit more subsequently. But as you can imagine, today's AI computation is all digital. We know that artificial intelligence is to replicate how human brain thinks. And we all know human brain is analog. Human brain is not digital. So if human brain thinks analog, then how can we learn from that and create an analog AI which can reduce power consumption significantly? As I described, today's models take megawatts of energy, versus our brain takes only 20 watt and still much superior model than any model that is created so far in the world of AI. So we are very excited about a long-term project along analog element. And then finally, we have to build system, because that's how we run AI model. So we are working on building systems, and I'll describe that a little bit more to you, what type of systems we have built to accelerate use of AI or chip technology, system technology, so that we can develop AI model at much lower cost and much lower power compared to where we are today. So as a part of building technology for AI, we have put a very ambitious goal of improving compute efficiency by 1,000 times in 10 years. That's the goal we set when we started our journey in the space of building more efficient and better semiconductor hardware. And that's how AI and semiconductor connects, that these need to be chip, algorithm, system that can provide us several orders of magnitude improvement in compute efficiency. Because the demand for AI workload will grow, it's growing faster and faster. That means opportunity for us to innovate is also growing bigger and bigger. It will have both impact to economic growth as well as national security, because semiconductor and AI and quantum are the technology that are of national interest. So in the roadmap that we created for next 10 years to achieve 1,000 times improvement, we have two broad categories that we focus on. Start with the digital, because that's the world that we understand. So we started with developing a technology which we, at IBM, we had pioneered. We call it approximate computing, and I'll describe that a little bit more. We build digital AI cores or digital chips that can benefit from use of reduced precision. And I'll describe that a little bit more. So that's our step one. That will give us as much as 10 times improvement, at least 10 times improvement in compute efficiency or power reduction. And then longer term, we are working on analog AI, which can give us 100 times improvement on top of it in terms of compute efficiency. So we have developed a very ambitious roadmap in that journey, leveraging all of our knowledge, our partners' experience, our academic partner, industry partner. In that journey, there are 3 steps that we are going through. Step 1 is the reduced precision arithmetic that I described earlier on. And I'll go a little bit more deeper into that. What is a reduced precision arithmetic? Just to give you an example there's a picture there on the screen in the reduced precision arithmetic. For a human being to recognize that picture, you do not need very, very high quality picture, because we can recognize picture using low quality image. In other words, we can get to the same answer with less information. What it means is that we can reduce the precision and get the same accuracy. That's the other language. That in the world of AI, we are not looking at high precision computing. We are looking at getting the same answer. Can we recognize the pattern? Can we recognize a picture? So that's the step 1, where can we live with less number of bits or lower precision. At IBM, since we have expertise in every aspect of chip technology, we can then design the chips that can really leverage the power of reduced precision arithmetic. The next step is the heterogeneous integration, where in the journey of digital world, can we start to put more cores or bring memory closer to logic by using 3D integration or chiplet technology. So that will be a semiconductor innovation beyond design into advanced packaging or chiplet technology. So that's our step 2 that will continue to grow improvement. And then the third step is the analog computing, where it's a mixed digital analog. The outside world is still digital. The chip have to still engage with other chips in a digital manner. However, can we perform computation in the analog domain by leveraging the material innovation? Because that's where, can we perform computation in memory? That's where it comes down to. Instead of performing a computation and memory separate, like moving data from memory to compute, back to memory, which is a traditional computing, can we perform that computation in the memory itself, or compute in memory for extreme efficiency in terms of power reduction? Now I'll go a little bit more deeper into reduced precision computing, where today's traditional computing uses anywhere between 32-bit to 16-bit for training and inference. However, we have been working on developing a new math, a new algorithm, so that we can use less number of bits to get to same result, both in the form of training and inference, again, without losing accuracy. As you can see on the right-hand side, the amount of information we have now for that picture is very small. Still, a human brain can recognize that picture because of the understanding, because of the algorithms. So we have been showing every few years that we can continue to reduce the number of bits that we use to perform those computing, or AI computing, which is a different type of computing than a traditional high precision computing. And then we are learning new techniques like quantization, sparsity, etc., so that we can continue in this journey. And with that, every time you reduce the number of bits by 2x, you are reducing, or its impact is 4x in terms of either the silicon area or power consumption. So you can see how we can go on this journey step by step, prove it in algorithm, and then translate that into a chip. That's the two-step journey. So as a part of, we always believe in not only that we do the right math and understand how AI computing gets done, but we also want to build hardware, because we have to prove that in silicon. So as a part of that effort, we build a hardware called Artificial Intelligence Unit, or AIU, using low precision computing, which provided 10x improvement in energy efficiency. As you can see on the right-hand side, it uses 32 AI core, and it can plug into a standard PCIe slot. And it supports data format all the way from floating point 16 to int 2. And as you can, now the models are generally trained in higher precision, but then you have to perform subsequent actions so that you can translate that model into a low precision. And then you can run that on this chip. You can also run it in high precision, but it will cost more energy. And if you run it with 2 bits or 4 bits, then it will cost much less energy if you use that data format. We started with this AI chip focusing on inferencing and fine-tuning for generative AI workload, because that's where the biggest demand for silicon will come. And then we are on that journey. So we had introduced this low precision core into a microprocessor in 2021, where we had 1 core. Since then, we have built a multi-core chip with 32 core, which is all focused on running deep learning model, which are faster and more efficient than general purpose CPU. And then now I'm going to start to talk about the system, because chip has to then translate into a system, and we are starting to build in IBM research artificial intelligence unit-based system that can then be deployed at a much larger scale to show significant reduction in power consumption or improvement in efficiency at the system level to meet the demand for the AI workload. So again, as you can see, the semiconductor technology and the AI technology, they are both connected. And that's how we will drive the improvement in the computing space. Now, AI is looking at computing from the workload, from application side. What it means is that we have to really not only invest in the hardware technology, but we have to also invest significantly in the software technology. We have to make the use of this AI chip easier and easier for the developers who are developing application or algorithms for AI. In that journey, we have partnered with framework called PyTorch. PyTorch 2.0 framework is how the AI, I'll say that is the entry point that we are using for AI practitioner to be able to use the efficient hardware that either we are developing or many other companies are developing. Because AI is so important and it's such an early stage that we believe there will be many companies who will come up with a brilliant AI chip, which will be better and more efficient. And we want to help and we want to participate so that all of those AI chips that are getting developed can use open source or a common software. And PyTorch 2.0 is where the industry is betting, and more AI chips are using PyTorch 2.0 as the entry point to be able to use the AI chip, which is underneath that. So as you can see here, I've shown the stack where we still have to work on our own driver and things which are very closely connected with hardware, but everything else we can offload to the PyTorch community and connect our hardware with the PyTorch framework, so that broad community can get benefit. And this framework can, as I mentioned earlier on, will enable many other AI chip to be made available for use for broader community. Now to look at how the things get built, always start from chip. So at the leftmost side, you can see the chip. Then a chip gets converted into a card that we call it AIU PCIe card. Then you have to put a heat sink around it because it still consumes power. From the card, then you build a node where this is like a many cards, like as many as 12 cards, which are performing AI computation, because now these nodes or servers are designed for the AI workload itself. Then you build a rack where you put many of these servers together, and then you build a cluster where you have many racks together, almost like a data center designed for AI. And now you can see how you build the AI compute capability based on understanding of the AI need, understanding of algorithm, understanding of how do we convert that into a chip design and then chip technology. We are very proud to share that we have built an early prototype of this extremely efficient AIU system. This is a scalable system architecture. It's highly power efficient. And I'm proud that Nishikawa-san had an opportunity to visit us a few weeks ago, where we were able to show him how quiet this system is and how low power consuming the system is. And we are running the workload on this system, AI workload on this system right now. As you can see here, this is the system, which is full, many racks. It's a IBM Research prototype on-prem system, which is deployed in Yorktown Heights, our headquarters. We are measuring, which performs, which is measured at a very high performance. We are running the same workload for AI. However, the very important part is that it's consuming much less power compared to traditional AI systems. Why? Because we focused on innovation at every level. We focused on chip level innovation. We focus on design, process technology, chip design, algorithms, and system design. We need to put all of this together to be able to generate the value that we need for an efficient or a sustainable future of computing. So this is the near-term or digital part of our journey that we are on. We have developed a roadmap where next step would be to use advanced packaging technology from where we are today, which is a SoC, a system on chip using advanced logic technology. Next step is to build, bring more memory together, or high bandwidth memory close to the AI chip that can reduce or that can enable us to run bigger and bigger models, because model size are increasing in hundreds of billions of parameter, leveraging some of the advanced packaging technology. And then longer term, we will use 3D chip technology to bring memory and logic chip together. That's the near-term roadmap that we are working on, again, towards a high-level goal of 1,000 times improvement in 10 years. That's what our journey is, and we are making progress every year, again, in partnership with many collaborators across the board. Now I'll switch gear to the next part, which is the analog AI, which is really exciting. It's actually changing the way we think about computing. Analog AI can provide as much as 100 times improvement in energy efficiency, because we are going to perform computation in memory itself. As I mentioned earlier on, look at the way our brain works. Our brain works like analog. Our brain is not digital. How can we learn from that characteristic and transfer that into a chip technology? But what it requires innovation at the materials level. And think about how we are again connecting a material, a semiconductor process innovation, to an analog AI chip. What we are doing here is performing basic computation like multiplication and addition using very simple functions like Ohm's law and the Kirchhoff's law, which is a very simple way of performing those computation as compared to traditional method of doing digital computation, where you have to move a lot of data from memory to compute and back from compute to memory with many, many thousands of cycles to perform one compute function. So some of the benefit of in-memory computing, analog in-memory computing, are improved energy efficiency. It can perform significant computation, complex computation. It also provides very low latency and almost zero standby leakage power. And as you can see on the right-hand side, we can map a deep neural network into a circuit and then develop this synaptic element, which you can see on the right side, which is, in this case, we are using phase change memory, where we can change the phase of memory to store information and then perform computation using Ohm's law, which is just you multiply resistance with current and you get voltage. You can perform that computation in one cycle rather than thousands of cycles that we have to go through. And some of the work that we have done in this space has been recognized worldwide. One of our paper where we actually built analog AI chip in 14 nanometer technology, and we were able to demonstrate speech recognition and transcription using analog AI technology. This was published in Nature just this year. As well as on the right-hand side, you can see that we had a paper on 64-core mixed signal in-memory compute chip based on phase change memory for deep neural network inference. That was a work that was published in Nature Electronics this year. So we, as IBM Research, are progressing the state of art in the space of next era of AI, which will be the analog AI. It's a little bit longer term research, but our role is to perform both near term, mid-term, and long-term research so that we can participate in the journey to build computing which is sustainable and can meet the economic and national security needs as well. So with that, I will conclude by saying that let's create the future of sustainable computing together. It takes all of us. It takes industry, government, and university, or we call public, private, and academia, working together. And the idea of bits, qubits, and neuron, that is traditional computing, AI computing, and quantum computing, is all coming together. Semiconductor technology is at the heart of all of those three computing. And we are just at the beginning to get so much benefit for both economic growth as well as for the national needs. Thank you very much for listening to my talk.